All right, today we're going to talk about something that every single C programmer bumps into, but maybe doesn't fully understand: program memory. We're going to pull back the curtain and really demystify what's happening under the hood when your code hits run.
Ah, yes. If you've spent any time with C, I am positive you've met this guy, the dreaded segmentation fault. It's that error that just stops your program dead in its tracks and can be a real pain to figure out.
So what is it actually saying? Well, in the simplest terms, your program tried to step into a part of memory where it wasn't invited. It's kind of like trying to barge into a locked room. To stop getting lost and to avoid these crashes, what you really need is a map, a blueprint of your program's memory.
Okay, so let's unfold this map. You might think of memory as this big, chaotic jumble, but it's actually the opposite. A C program's memory is a super organized structure, neatly divided into different regions or segments. And understanding this map is, seriously, the first step to becoming a master of memory.
Think of it like we're taking an architectural tour of a building. We're going to walk through each floor, check out what each room is for, and see what's stored inside. So let's start at the bottom and work our way up.
First, we're going to start with the foundation. These are the parts of your program's memory that are static. They're set up the moment your program loads, and they stick around for the entire time it's running. They don't change.
First up, we have the text segment. You might also hear this called the code segment. This is the bedrock, the concrete foundation of our building. It's where the actual compiled machine instructions, the brain of your program, live. And here's the crucial part: it's read-only. That's a super important safety feature, right? It stops your program from, accidentally rewriting its own instructions while it's trying to run them.
Next door, we have the data segment. This area is home to all your global and static variables. This is the stuff that needs to hang around for the whole life of the program. But here's the thing, it's not just one big storage closet. It's actually divided into two very distinct, very important subsections. And this is where it gets really interesting. On one side, we have the initialized data segment. This is for any global or static variable that you give a starting value to right in your code, like int global var equals 10. But on the other side, we have the uninitialized data segment, which has this old school name, BSS. This is for globals and statics that you declare but don't give it an initial value. The system just says, okay, I'll make sure these start at 0. And this separation, it's actually a clever optimization to make your program load faster.
All right, we've seen the static foundation. Now let's head upstairs to the floors where all the action happens. We're talking about the dynamic duo, the heap and the stack. Unlike the code and data segments, these two are constantly changing, growing, and shrinking while your program is running.
Let's start with the heap. This is your program's wide-open, flexible workshop. Whenever you need to create something on the fly, and you don't know how big it's going to be when you're writing the code, you ask for space from the heap, usually with a function like malloc. You, the programmer, are in charge here, and you got to remember, the heap grows up towards higher memory addresses.
And growing from the complete opposite direction to meet it is the stack. If the heap is a flexible workshop, the stack is a super organized, super efficient office. Every single time you call a function, a new stack frame gets slapped on top. This little frame holds everything that function needs: its local variables, any parameters it was given, and where to go back to when it's done. Then when the function finishes, pop, the frame is gone. It's lightning fast, it's all automatic, and it grows down.
And this simple little diagram shows the central drama happening inside your program's memory. You've got the heap growing up and the stack growing down, moving towards each other in the same address space. If they ever collide, game over. You're out of memory. That's when you get a dreaded stack overflow or a failed memory allocation.
So that's the theory. That's our map. But talk is cheap, right? How can we be sure this is what's really going on? Well, we can actually look for some proof. We can see these segments with our own eyes and even watch them change.
We're going to use a handy little command line tool called size. It's awesome. It tells you the exact size in bytes of the text, data, and BS segments in your compiled program. So we're going to run a quick 3-step experiment to prove our map is accurate.
Okay, step 1. We compile the simplest C program you can possibly imagine. It literally does nothing, and we run size on it. This is our baseline, our before picture. As you can see, we've got some numbers. The text segment is 960 bytes, data is 248, and BSS is 8. Got it? Now let's start changing things.
For step 2, we're going to add just one little thing: a single, uninitialized global integer. Now, according to our map, where should that go?
It should go in the BSS segment, right? And look at that. The size output is perfect. Text and data are exactly the same, but BSS has grown to 12. It went up by 4 bytes, the exact size of an integer on my system. It worked just like the map said it would.
And now for the grand finale. We take that same global variable, but this time we give it a value. We initialize it, so it's not uninitialized anymore. Now where does it go? Check out the result. The BSS segment shrinks right back down to its original 8 bytes, and the data segment grows to 256. The variable literally packed its bags and moved from the BSS room to the data room, exactly as our blueprint predicted. How cool is that?
Okay, so that was a neat little experiment. But you might be thinking, so what? Why do I need to know this? Well, trust me, this isn't just a fun fact for a trivia night. Understanding this blueprint has real practical consequences for how you write code every single day.
So why does all this matter? Because with this map in your head, you're a better programmer. It's that simple. When you hit a segmentation fault, you're not just guessing anymore. You have a mental model of where your program might be trespassing. You'll understand that those pesky memory leaks, that's a heap problem, and you'll know how to manage it. You'll start writing tighter, more efficient code by making smart choices about where your data lives. It's about gaining this deep, fundamental understanding of what your code is actually doing.
You're not flying blind anymore. You have the architectural blueprint to your program's memory. And this knowledge doesn't just help you fix bugs, it empowers you to be a smarter, more deliberate, and more effective coder. So the only real question left is, now that you have the blueprint, what are you going to build?